Okay, so here is the distribution of the grades. If you want to know kind of the average was about a 68%. Normally the average is around 72%, so this is a little low for a class like this. However, it's not so surprising because of the accelerated pace. I know some of you don't have or didn't have your books yet. There's a lot of factors that could lead to some people doing lower on the first contest because of just not having as much time to get ready, and so hopefully it will improve. These grades are A's, these are B's, these are C's, this one is a D, and the rest are F's. So pretty widespread of grades. I want to say a few things about the contest. I have solutions which I will post after class. I meant to post them before class, but I didn't. I just realized I didn't post them yet. So that you can look at the solutions and kind of compare your work to the solutions. And then after you've done that, if you have questions about anything, then you can set up a time to meet with me and collaborate, or that's probably best. I'm not really supposed to give a lot of detailed information about grades in emails for privacy purposes. So schedule to meet with me and collaborate, and I can go over anything, questions about your contest. But let me make a few overall comments now that we've seen one contest. First of all, if you got an F on this contest, for example, that does not mean you cannot pass the class. It doesn't even mean you can't do well in the class. I've had students who got an F on the first contest and still got an A in the class. So it really depends on you going forward. However, if you got an F, there are different reasons you might have gotten an F. Or let's say you just got a C, but you really want an A. So I want to talk, now that we've seen a contest, about how to prepare for the other contests. We have 7 more contests. So this is a small fraction of the total grade. So don't worry too much if your first contest didn't represent the amount of work you put in. If you did badly and your first contest did represent the amount of work you put in, meaning you didn't put in any work, then you got to change some stuff real fast. Okay, several people through the last week, even today, have emailed me saying, I don't have the book yet. Can you send me pictures? So I've got a couple thoughts on that. First of all, these books are really cheap. It's only on Amazon, I think, $40 for the 2 books. So why not spend an extra $10 and have it delivered, in a day or 2? I don't understand that. I really don't. In your lifetime, getting an F in a class is probably going to cost you tens of thousands of dollars. I mean, really, that's honestly, and you're saving $10 on shipping. I don't understand that at all. And Dustin is sending a link. That's probably a PDF of the book or something. There you go, PDF of the textbook. So there's no, really, I tried my best to make this an affordable thing, and part of the reason is so you shouldn't wait 2 weeks to get the book for the class. You're wasting the tuition at the very least. You're spending hundreds of dollars, maybe thousands of dollars on tuition for your classes this summer, and if you don't get the book and you fail the class, what's the point? So get the book, use Dustin's link. I don't know if you have a link for the other book or not, but I'm sure that stuff is available. Chegg has copies of books, and they're out there. Okay. Yes, if you don't have the book yet, get the book. Okay. I normally give a talk after the first contest because the first contest is generally a shock to people. And some people do very well on the first contest, and then they don't do well the rest of the class because they think, oh, this class is easy. Some people go the opposite way. They don't prepare for the first one. They realize this class is actually hard and they have to put a lot of work in, and their grade, goes up and they do very well. There's basically three approaches I've seen to studying physics, and the summer class being accelerated and being online, there's probably, maybe this isn't all 100% applicable, but there's one group of students who typically come to class every day, take notes, pay attention to the lectures, carefully. In the online format, I would say this group of students are the ones that either attend the online lecture every day or watch all of the videos, not the night before the contest, but on a daily basis to try to stay abreast of things. And those students are paying close attention, and what we're doing in class is making sense. And so that group of students kind of says, okay, I think I'm feeling good about this, and so doesn't do all the homework necessarily. And if you're in that group of students, well, that group of students is over here. Okay, you're going to get an F in this class. If you watch every video or you attend every lecture and you nod because it's all making perfect sense, then you do nothing else after that, you will get an F in this class. That is virtually a guarantee. Okay. Second group of students doesn't come to class all the time or doesn't watch the lectures, but does do the homework. Okay. That group of students, the students who don't watch the lectures but just sit down with the problem books and work through the homework and just try to figure it out, that group usually gets a B or a C. So what I'm telling you here is, if you have to make a choice between doing the homework and watching the lectures or watching the videos, you want to be over here. You should be doing the homework. It is more important. What you're doing at home outside of class is more important than what I'm doing. And if you're watching the lectures but not taking notes, you're wasting hours and hours of time. If your pencil's not moving, you're not learning anything. Okay? The third group of students are the ones, as you might guess, who watch the videos or come to the lectures, ask questions, take notes, feel like they're understanding something but not everything, and then sit down and do the homework. Okay, if you do that, you probably wind up about here. Okay, somewhere in the A to B range. And where you are within the A to B range depends on a lot of factors. How much extra time you put in, what your math skills are like, how much work. But you really are not going to be successful, even in the regular semester where you have 16 weeks. This is true. Now, when you only have 8 weeks, you cannot learn this stuff. I cannot vomit forth knowledge and you guys just get covered in it and now you know physics. And there's really nothing that you can learn this way. If you can learn anything this way, it must be extraordinarily easy. If you watch YouTube videos on how to knit, you can watch lots of YouTube videos on how to knit. And if you then decide to go out and invest and you buy $100 worth of fancy yarn and buy some knitting needles and decide to just sit down, you're going to knit a sweater, you're going to waste a lot of money and have a big tangle of yarn, because you can't learn just by watching other people do something. And the same goes for physics. If you just watch me solve problems or you just read the solutions in the book, or you watch Khan Academy videos, all that happened, you come away feeling good, like you learned something, but you didn't learn anything. Okay? Now, I'm sorry, it sounds like I'm giving you a lecture. I'm not trying to give you a lecture. I'm just trying to make a very strong point. It doesn't matter if it's knitting or playing guitar. I play guitar. I can watch videos of people playing guitar lots, and I enjoy it. And I even, because I played guitar for a long time, I think, yeah, I kind of see how that works. But if I don't actually sit down and pick up my guitar and try to play and practice and practice and practice more, even with somebody showing me note for note on a video what to do exactly, I still can't just play something without picking up my guitar and getting my, playing until my fingers hurt. And the same goes for this. You cannot learn it without sitting down and doing the homework and making mistakes and, asking for help. And I mean, you're not gonna get it, okay? So this is normally what happens on the first contest, and a lot of people kind of hear this and they see what happened and they realize, oh God, I thought this is going to be easy. Why do you think physics class is going to be easy? I don't know, because that's not the reputation it has. But it will be easy if you do the homework. Okay, if you do the homework, everyone in here can easily get an A or a B. But if you don't do the homework, everyone here can easily get a D or an F. And it has very little to do with how brilliant the lectures are or how boring. It has to do with how much work you put in. So, okay, that's the only time I'm going to give you that talk, and I'm only doing it in the hope that a few of you who got these low grades got low grades because you did not do the work. So going forward, if you didn't do the work and you got a D or an F or even a C, but you think you should be an A student, then it's really clear what you should do. You have to do the work. If, on the other hand, you did the work, you came to the lectures, you did what I'm saying you should do, and you still got a grade in here, you should talk to me immediately so that I can help you figure out what is going wrong. Okay, and there could be some easy things to fix that are going wrong, but they will not fix themselves. So if you did all the homework and you did not receive a passing grade, you should talk to me, directly after class or sometime today, as soon as you can. Okay. Now, does anyone have any questions? So please take note. In the chat, there is a link. I don't know if I can't really post it onto the whiteboard, but and I really can't post this link officially on Blackboard either because I'm not entirely sure the legality of that link. There's a link to the 3000 Solved Problems book if any of you are having difficulty getting a hold of it. Let me comment about the conceptual question on the contest because a lot of people who got C's could have gotten B's, or who got B's could have gotten A's if they got this right, or maybe just didn't pick it. So the question said, you throw something up in there, and it goes up, and then it comes down. And at the top, this could be a graph of x, which would be its height above the ground versus t. At the top, what's going on with the velocity acceleration? So I actually graded this fairly leniently because it is a multiple choice test, or problem anyway. And a lot of you got it wrong, but your answer that you chose was half right, and I decided to give you half points for that. So at the top, the velocity equals 0, but the acceleration is still negative g. It is a sad curve. The acceleration is negative. So many people picked v equals 0 and a equals 0. A is always the same. It's minus g during the whole path. The v is only 0 at the top. Even people drew this picture and still got it wrong. So that's that kind of shows you how tricky the conceptual questions are to choose on the contest. So I really recommend, some people only pass because they got this right. So that's one of the reasons I leave these on there. But if you have been doing homework and solving problems, I would say it's not worth the risk to pick a conceptual question as one of the questions that you want me to grade. Okay, so I'm not going to say anything else about the contest. After class, I will post the solutions. Please go over what I returned to you and look at the solutions and make sure you understand everything, because we still have to know this stuff going into the next chapter, and we have to know it at the final. So even if you are missing some things, you need to clarify that. And then if something's unclear, then set up a meeting with me. Also, make sure to count your points and make sure that it's entered properly on Blackboard, because sometimes there's a mistype or something. Okay. How many of you who are here did the lab already? Okay, so maybe most of you. Okay, good. I want to just bring it up for you to see, and I'm going to talk about it a little bit, not the lab, but I'm going to use this to demonstrate, and then we can begin talking about vectors and get ourselves ready for chapter 3. Okay, so this is just a sample of a vector that we are going to learn how to work with. And so this particular vector, it has a length of 40. So the magnitude of the vector is 40. It has an angle of 30 degrees, and it has what we would call the x component, or if we think in terms of math class, the adjacent side of this triangle is 34.6 units long, and the opposite side is 20 units long. Now, in terms of notation, what we have is the absolute value of the vector d, which means the magnitude of the vector d is 40. The angle theta is 30 degrees. D sub x, so d with a subscript x is the length of the x component, and d with a subscript y is the length of the y component. And what these are, to connect it with real life situations. If somebody told you to start where you are and move 40 meters at a 30-degree angle north of east. So if you're looking east, like toward the Mississippi River from where I am anyway, and then you turn to the left a little bit by 30 degrees and you walk 40 meters, you would have traveled effectively 34.6 meters to the east and 20 meters to the north. So these components are telling you how far east or west and how far north or south you go if you travel a certain direction, a certain distance. And the vector, lab assignment was really just to help us get familiar with how these things work, and in particular, how to add them. So if I have these two vectors, let me, well, that'll be fine. So one vector is 14 units long, points at a 25-degree angle, and it represents moving 12.7 units to the east and then 5.9 units northward. And then we have a second vector that is 15 units at a 60-degree angle. It represents moving another 7.5 units to the east and another 13 units northward. And if I wanted to know exactly where do I wind up relative to the origin at the end of this, all I have to do is add the 12.7 and 7.5. That would be, let's see, 19, 20.2 units to the east and add the 7.5 and the 13, and that would be 20.5 units. And if I display the sum vector, that shows me did I add that wrong? Oh, I added 7.5. 5.9 times 13 are the northward pieces. So that's 18.9 units to the north, and we're 20.2 units to the east. And the whole point of that exercise was for us to see that if I am given a vector, okay, if I'm given a vector, let me go ahead and just get back to one vector again. If I'm given a vector and I'm going to add it to another vector, it's not useful for me to know how long the vector is or the angle. Instead, I have to know the x and y components, the x and y coordinates of the tip of the vector. The only way we can add vectors is by adding these components. And so today, what we're going to learn, what the lab did not tell us, is how do we find those components. I mean, you could find it graphically by just measuring how far along in the eastward direction we are and sort of estimating in between the grid points how far to the north we are and estimating. But there's a precise mathematical way for us to work out those numbers. And that's what we want to know. Because in nature, there are a lot of quantities that are vectors. Displacements are vectors, velocities are vectors, forces are vectors, magnetic fields are vectors. You know, there's just a lot of vectors, and these things often get added up. For example, if you're flying an airplane, to know the velocity of the airplane, you have to know the plane's velocity relative to the air, and then you have to know the speed of the wind. So if you're flying maybe in this direction, represented by this purple vector, but the wind is a northward wind, then the actual direction you're going is the direction that this sum vector indicates. So on the other hand, you know, if you want to go due north, but you have a wind like this vector E, then you have to change your, let me see if I can, you have to change the direction of your airplane's velocity in order for the sum to wind up being due north. Okay, so this can happen in many contexts, whether it's building structures or flying planes, or dealing with electronic circuits, just all over the place. If you want to study the human body, some of you are wanting to go into physical therapy. There are forces and torques, which are vectors, which can lead to a twisting that causes injuries. So we need to understand the math of vectors, because it appears really throughout this course. So let me return to my whiteboard and start to talk about how exactly we find the components. Did anybody have any questions about anything related to the lab? Was there anything about vectors that wasn't clear? I mean, other than how to find components? That's not what I want. Oh, by the way, with regard to the labs, when I grade the lab, if you missed points, you are always welcome to fix your mistakes in the labs and resubmit it and get full points. So make sure to take advantage of that. The labs are really, the exercises are designed as sort of an exploratory thing to help us explore a topic, hopefully before we have to work with it in class, and get some intuition. And they're not really supposed to be punitive, punishing you for good work, or sorry, for bad work, or rewarding you for good work. Okay, so let's talk about vectors. I don't want that color. Okay, so suppose I have a vector, we can call that vector A. And suppose the length of A is 10 units, and it's at an angle theta, which is 30 degrees. And I want to know what are its components. And I can think of those components as saying, so, you know, vector A takes me from the origin to some location, which would be the point AX, AY. And what is the value location at that point? Well, I can imagine that I move some certain distance to the east and some certain distance to the north. So I can think of the vector A as being a sum of moving to the east plus moving to the north. And what I want to find is I want to find the length of these sides. And what we use, we make use of a property of triangles. First of all, this is a right triangle. It's always going to be a right triangle because the x component and the y component are always perpendicular to one another. We use perpendicular axes on purpose. So the property of similar triangles is that if I have that triangle and I have another triangle that is the same shape, it is similar, but it's this big. Say this one is vector B with the same angle. What I'm guaranteed is that if I take a ratio of any two sides, we can call this side AY and this side AX, and this side is BY and this side is BX. Because these two triangles are similar, it's guaranteed that the ratio of two sides on triangle A is equal to the ratio of the same two sides on triangle B. So for example, if I know that, let's see, the ratio AY over the magnitude of A, this has to be equal to BY over the magnitude of B. And let's just suppose that I knew that BY is 10 units. Okay, so if I know this triangle, then that's enough for me to determine the sides of a different similar triangle. If we take a look at this expression here, given that we know BY and we know B, the magnitude of B, and we know the magnitude of A, we can clearly find AY. We just would do that using by multiplying by the magnitude of A on both sides. This is going to be 10 times BY, which is 10, over B, which is 20, and that gives me 5. In other words, if this is exactly half the size of this, if BY is exactly half the size of B, then AY must be exactly half the size of A. Now, normally we're talking about the magnitude of a vector. We don't always, it's kind of burdensome to write absolute value of the vector A. So a different strategy, a different notation that we'll see a lot in the books is just to call this A and to just call this B. So in other words, if it has a vector sign over it, it stands for the whole vector. But if it's just a letter, then it stands for the magnitude of the vector. And I'm going to use that notation from now on because it's a little more standard. It's not exactly what was in the vector lab, but it is a little more standard. Okay, so coming back to it. If I just have one example of a triangle with a 30-degree angle, a right angle, and then, of course, a 60-degree angle, and I know the lengths of these sides, this one would be about 17.3. I just happen to remember this triangle. if I know this triangle, any similar triangle, I can figure out the lengths of its sides. Okay, so in this case, this would be 8.66 because the ratios are the same. Now, how do we know for a given triangle these ratios? Well, we can't figure that out really. We don't have access to that anymore. I mean, it can be worked out, but it's hard. Just like finding the square root of a number like 2 is hard. I don't know. I'm pretty old, and when I was in middle school, my math teacher was super old. So he actually taught us how to compute a square root by hand on paper, without using a calculator. Raise your hand if you learned how to do that in school. I've got to be the only one. Anybody ever learn how to find a square root on paper without a calculator? I hope not, because Katrina, you did learn how to do it?
Yes.
Okay, you must be like me. I don't remember how to do it, but I remember spending weeks doing it, and now I feel like those were weeks lost in my life because not only do I not remember how to do it, but I would never want to do it, even though I'm a math, and science person. Figuring out the ratios of sides of triangles is a bit like figuring out a square root. Yes, you can work it out on paper, but basically everybody who ever would have a call to use it would just look up the answer on a calculator, just like we look up the square root of 2 or something like that. So I actually have a book, it's upstairs, but it has tables with angles, 30 degrees, 30.1, 30.2, 30.3, every angle from 0 up to 90. And then it tells you the ratios of the sides of the triangles for a right triangle with that angle. And some poor students hundreds of years ago probably spent a year computing those things by hand. But we don't have to compute them by hand. We just need to know how to have access to that database. And we don't even look in this old book that I've got upstairs. We just punch it in your calculator because your calculator has the whole thing stored. So let's talk about ratios. So here's a triangle A and AX and AY with an angle theta, and it's a right triangle. And the three ratios we can have, this side AY is known as the opposite side. When we're talking about a triangle, this is opposite to angle. And this side AX is known as the adjacent, or just, ADJ, adjacent side. And this side, as you probably all know, is called the hypotenuse. Okay? And so the three ratios we can have is we can have the opposite over hypotenuse. We can have the adjacent hypotenuse. And we can have the opposite over the adjacent. So those are the three ways we could find ratios. The first one is known as the sine of theta, and the second one is named the cosine of theta, and this last one is called the tangent of theta. Okay? So what we need is calculator buttons that compute these things. And if we have those buttons, we can always find the components of a vector. So the buttons on the calculator look a little different. They abbreviate them. Sine is abbreviated SIN, sine theta. The cosine is abbreviated cosine of theta, or just cosine. And then there is the tan. tangent of theta. So this is what you should be looking for on your calculator, these buttons. And they will allow us to find the lengths of the opposite and adjacent and hypotenuse. Whatever we don't know, we can typically figure them out. So let's do a sample, and if you have a calculator, go ahead and get it out and learn how to use it now while I'm working. So first, I want to verify using the calculator. So let's call this A. If we have a triangle or a vector A, which forms a triangle with AX and AY, and I want to find one of these sides. Let's suppose I want to find the opposite side. The first thing I do is I say, okay, which trig function goes with the opposite side? So I look back here, the sine uses the opposite and the tangent uses opposite. But I want to use the sine because it uses opposite and hypotenuse, and I know the hypotenuse. I don't know the adjacent side. So we would write down sine of theta equals, the opposite over the hypotenuse. In this case, that would be AY over A. So sine of theta equals AY over A. And to find AY, I just multiply both sides by A. AY equals A times the sine of theta. In this case, that's 10 times the sine of 30 degrees. So you get out your calculator, you find out that the sine of 30 degrees is 0.5. And so your calculator should tell you that. Go ahead and try that on your calculator and raise your hand if you get 5 for 10 times the sine of 30. Okay, a lot of you. Did anyone get something different? Because sometimes your calculator needs to have a setting changed in order for you to get this. Anybody having trouble with your calculator? Okay, so we can do the same thing. Sam, you have your hand still up. Is it just still up, or do you have a question? Okay, just still up. So then we can find the x component. So again, I ask myself, which trig function relates to the x component? Well, that is the adjacent side. Adjacent means next to. It's the one that touches the angle, but is not the hypotenuse. Hypotenuse is always the longest side. The hypotenuse is opposite the 90-degree angle. And the adjacent side is the one that touches the angle that is not the hypotenuse. So I go back and I look and I say, okay, the cosine uses adjacent and the hypotenuse, and the tangent uses opposite and adjacent. Well, we now know the opposite side, so we could use the tangent, but we also know the hypotenuse, and we could use the cosine. I would recommend we always use only the sine or the cosine and never use the tangent for finding the x or y components. So the cosine of theta equals the adjacent side, which is AX, over the hypotenuse, which is A. And to get AX by itself, we just multiply both sides by A. So AX is going to be A times the cosine of theta. In this case, that's 10 times the cosine of 30 degrees. And if you put in cosine of 30 degrees in your calculator, you're going to get 0.866. So this gives you 8.66, or you might get square root of 3 over 2, depending on the setting of your calculator and how fancy your calculator is. I prefer just getting a decimal number. Okay, so what we just did was we took a vector where we knew the magnitude and the direction. This is like what happens with the pink vectors in the lab, the D, E, and F vectors. we start off kind of picking a magnitude and direction, and it tells us the x and y components. And that's what we're doing here. If I wanted to add this vector to some other vector, I would have to go through this process. Any questions about the process so far? Okay. Ziad?
Does it matter if we get an answer with like a square root in it?
It doesn't really, but generally when we're solving problems in physics, we're not going to necessarily have nice numbers like 10 anyway. So if the vector A is like 13.6 units, and then you multiply 13.6 times square root of 3 over 2, you're going to get a decimal number at the end. So it's not really beneficial to keep the square root of 3 over 2. Also, I'm picking the angle 30 because it's a well-known triangle, and I know the values sort of off the top of my head, but in real life, it's rare that you're going to have exactly a 30-degree angle. So generally, we're just going to have some decimal expression. I'd say 99% of the time.
Okay, thank you.
Sure. Any other questions? Okay. So there's a mnemonic device that a lot of people use to remember the names of these ratios. So these ratios are called the trig functions. And again, I'm going to just the sine of theta is opposite over hypotenuse. The cosine of theta is the adjacent over the hypotenuse, and the tangent of theta is the opposite over the adjacent. Okay, so those are the names of them, and the mnemonic device is called SOHCAHTOA. SOHCAHTOA. I know it sounds like you're cussing someone out in Russian, but it's really the mystic mathematical phrase. SOHCAHTOA. Sounds harsh, but SOHCAHTOA. A lot of people in this class have probably learned these things before, and a few people probably have not. And I'm gearing this more toward people who have not seen this. So if you already know all about SOHCAHTOA, and some people learn this expression to memorize these, and other people somehow memorize it without that expression. If you've learned it already, that's great. That's good news for you. It means your homework for tonight is going to be, extra easy. And if you've never seen this before, that's okay. But you are going to have to learn how to do it tonight by practicing. Okay? And it's not going to be enough to just watch this lecture. Now, you can go back to the web page of the lab and use it as a tool when you're doing homework and adding vectors. You can add them on that lab, and that would be a good way to check your work. Okay, but don't add them on the lab to get the answers, because the homework is not about getting the answers, it's about learning a process. Okay, so now in general, the tasks we have here have a vector A with an angle, and we could write this as AX and AY. So these are two different descriptions of a vector. This one is called the polar form. And normally when we find a vector in nature, it comes in the polar form. We know its magnitude and its direction. We find out the wind speed is 32 miles per hour north by northeast, or something like that. But if we want to actually work with them, we need this other form, which is called the Cartesian form. So your goal really for today and tonight is to be able to take a polar form vector and turn it into a Cartesian form. Meaning, if we're given the hypotenuse and the angle, we need to find the adjacent and the opposite side. We also need to be able, given a Cartesian form, AY and AX, we need to be able to go backward and find the polar form. This is because when we report the answer, after maybe adding some forces together, we usually want to know how big the total force is, which would be the magnitude of the sum of the forces. And we want to know what direction that sum of the forces is pointing. So we have to be able to go both ways. We have to be able to go from the polar form to Cartesian form, and we have to be able to go Cartesian form to polar form. And in between those, we need to be able to add vectors. So those are the three tasks we're really working on today. Getting polar form, from polar form getting Cartesian form, from Cartesian form getting polar form back, and also adding vectors. Okay? Now, to go from Cartesian, let's go to a new slide. We're going to do a little bit more and then take a short break. Okay, from the Cartesian, that's like Descartes, Cartesian. To go from the Cartesian form to the polar form. So what does that look like? It looks like we have a triangle, maybe with 5 here and 8.66 here, and I want to know the angle and the magnitude of the hypotenuse. So how do we do it? Does anyone know how first to find the magnitude of the hypotenuse if you know the other two sides of the triangle? Raise your hand if you know how to do that. Okay, few people, maybe 5, 6. So someone tell me how you do that. Elise?
Is it the Pythagorean theorem?
It is. Can you remind us what the Pythagorean theorem is?
A squared plus b squared equals c squared.
Yeah. So if we have a triangle with sides A, B, and C, where the hypotenuse is C, then the Pythagorean theorem says A squared plus B squared equals C squared. The Pythagorean theorem. Pythagoras himself had nothing to do with the Pythagorean theorem, but his followers, the Pythagoreans, did it. And so in this case, this would say that A squared equals AX squared plus AY squared. So that would be 8.66 squared plus 5 squared. And we typically want to take the square root. So try that out in your calculator, and let's see what we get. I get 9.9998, or really, it's 10. And remember, that's the triangle we started off with. We started off with 10 on the hypotenuse and 30 degrees for the angle. But what if we only knew the sides, the 5 and the 8.66? Well, we can find the hypotenuse using the Pythagorean theorem. And then we have to try to find the angle. Okay, so finding the angle is the part that people are usually not so familiar with. The Pythagorean theorem, most people have seen that somewhere. Even if you didn't remember it at the time, you've probably all seen the Pythagorean theorem and used it many times. Now, finding the angle is a little different. Remember, to find the trig functions, the sine or cosine or tangent, we go sort of historically, we go to this old book. It was musty, moldy old book and we start flipping through it and we look for, say, 25 degrees, and we find what the sine of 25 degrees is. Well, we can use that book backwards. We can go through the column that says sine of theta. In this case, I know that the sine of theta would be opposite over hypotenuse. That's 0.5. So if I have access to that table, I just go through the sine of theta column and I see some number is 0.4 and 0.45 and 0.6, 0.7, 0.8, 0.9. And finally, I find a number 0.5. Sine of theta equals 0.5. And then I just look across and see what angle was that. This is kind of like a reverse phone number lookup. You have a phone number and you want to know, some place keeps calling you and you want to know what it is. So you put the number in and you find out the place instead of putting in the name of a place to find its number. So that's exactly what's happening here. Now your calculator has a built-in button for the reverse lookup. This is called the inverse sine. It looks like sine with a -1 on your calculator. If I do the inverse sine of the sine of theta, that would be the inverse sine of 0.5. On paper, this is what it looks like. The calculator, you put in inverse sine of 0.5, and it's going to tell you 30 degrees. On the left-hand side, if I have the inverse sine of the sine of theta, the inverse sine and the sine, you can think of them as just canceling and leaving me with theta. So the inverse sine is a lot like a square root button. If you have, like, x squared equals 5 and you want to know what x is, you do the inverse of square function. You have x, and then you square it to get 5, and so you want to do the inverse or unsquare it, the square root. So the inverse sine is sort of undoing the sine. It's reversing or canceling the sine. So this is how we could get it, but in general, we won't want to use the sine. We're going to want to use the tangent. So generally, this is how I would do it. I just know that the angle is going to be the inverse tangent of the opposite over the adjacent. That's going to be AY over AX. That's the inverse tangent then of 5 over 8.66. And if you put that in your calculator, do the inverse tangent, I get 30.0007. Really just 30 degrees, but because I have rounded off my 8.66, I have a rounded off angle. Okay, so we're actually going to always use the inverse tangent for finding angles, 100% of the time. And after we take a break, I'm going to explain why we always want to use the inverse tangent instead of an inverse sine or cosine. But for now, let's take a break, maybe a 5-minute break, and then when we come back, we're going to keep working on this. Stopping record. Any questions before we take a break? Okay, stopping the recording then.